Over molecular geometry. By the end of the tutorial, you should be able to answer the following questions. Draw the Lewis structure for methane, sulfate, and carbon dioxide, including any resonance structures that's needed. Calculate the formal charges for methane, sulfate, and carbon dioxide. Determine if methane, sulfate, and carbon dioxide are polar or nonpolar. Determine the molecular geometry for methane, sulfate, and carbon dioxide. And tell me which type of intermolecular force is the strongest. So Lewis structures. Lewis structures indicate the shapes of molecules by showing the bonding of valence electrons. And you remember how to draw Lewis dot diagrams. Carbon has got 4 valence electrons, and hydrogen has 1. So covalent bonds share, so they can share these two and form a bond. And we could do that with another hydrogen. And they could share those two and form a bond. And so instead of drawing it weird like this, we just indicate a single line, and it represents 2 electrons. So here are the rules for drawing molecules. First, you need to add up all your valence electrons from all your atoms. Then form bonds between the center atom and the outer atoms. The least electronegative atom goes in the center. Then you distribute the remaining electrons to satisfy the octet rule. And the octet rule says that everybody needs 8 electrons around them. So everybody wants 8 electrons. And they do that so that they have a full valence shell like the noble gases. If you're doing a Lewis structure for an ion and the charge of the ion is negative, then you add however many electrons to the sum of your valence electrons. If the charge of the molecule is positive, then you subtract from the sum of the valence electrons. Resonance structures. So if more than one Lewis structure is possible, then the molecule or ion is said to have resonance, meaning it can be in different places. So like if you have a double bond between this carbon and oxygen, these electrons could also go here. They could also go here, be on this oxygen, or be on this oxygen. So it's like it could rotate around the molecule. And if you can draw resonance structures for a molecule, then you have to. Dipoles. The more electronegative the atom, the tighter it will hold its electrons close to the nucleus and creating a dipole, meaning one end of the molecule will be positive and one end will be negative. So in water, there's these 2 lone pairs here of electrons. And oxygen is very electronegative. You have to remember your electronegativity trends from the periodic table. Hydrogen's over here. It's not very electronegative. Oxygen's over here. It's very electronegative. So it's going to kind of hog the electrons. So we draw this arrow pointing towards the more electronegative, and then we make like a little positive sign here indicating that this side of the molecule is more positive. And you could do that for bonds too, because sometimes you can have polar bonds but not necessarily a polar molecule. So here carbon is going to be a little more positive because fluorine is very electronegative, and it's going to kind of want to pull all the electrons toward itself. Now here again, oxygen is electronegative, more electronegative than carbon, but because we have two oxygens pulling in the same direction, these dipole moments are canceled out and the overall molecule is nonpolar. Now the bonds are polar, but not the molecule. Okay, so like I said, a polar molecule always contains polar bonds, but some molecules with polar bonds are nonpolar. A molecule in which the bond dipoles do not cancel each other out is a molecular dipole. So here, chlorine is more electronegative than carbon. So this bond, this bond will be polar, but I've got 4 of them, and they're all equal because it's all chlorine. So they all cancel each other out, and this molecule is nonpolar. Carbon tetrachloride would be nonpolar. Now nitrogen, this is ammonia. Nitrogen's more electronegative than hydrogen, so these bonds are polar. And we have a lone pair up here, a lone pair of electrons. They're non-bonding electrons. And so this region of the molecule is more electronegative. So this would be a polar molecule, because overall there's more electrons up here. Okay, formal charges. In order to decide which Lewis structure is the best, because sometimes you could satisfy the octet rule drawing more than one Lewis structure, you have to calculate your formal charge and make sure your formal charges are low. So you take your valence electrons, subtract your half of your bonding electrons, and subtract your lone electrons, and that will give you your formal charge. And you have to do this for each atom. So let's start with nitrogen. How many valence electrons does nitrogen have? You have to look on your periodic table. It has 5 valence electrons. Okay, how many bonding electrons does it have? Well, each line we said was 2, and we want half. So just count each line as 1. So 1, 2, 3, 4. So 5 minus 4. Are there any lone electrons? Meaning, see these dots right here are lone electrons on nitrogen. No. So 5 minus 4 minus 0 is 1. So this nitrogen has a formal charge of 1. Let's do this oxygen right here. How many valence electrons does oxygen have on the periodic table? 6. Minus the bonds, 1, 2, minus our lone electrons, 1, 2, 3, 4. 6 minus 2 minus 4 is 0. So this particular oxygen has a formal charge of 0, and nitrogen was 1. Okay, we have to do it for this oxygen. Oxygen has 6 valence electrons. It has 1 bond, so minus 1. And then it's got 1, 2, 3, 4, 5, 6 lone electrons. So it's negative 1. So this particular oxygen, negative 1 charge. Now I'm going to do the other one. 6 valence electrons for oxygen, 1 bond, and 1, 2, 3, 4, 5, 6 lone electrons. So this one has a negative 1 too. So this is a pretty good structure for NO3, or nitrate. Now, could I have drawn resonance for this structure? Yes, because this double bond could have been over here, or it could have been over here. It could have moved. So I should have drawn resonance structures for this molecule. Okay, shape. So these Lewis structures tell you kind of where electrons are going to be, and it gives the molecule a shape. And we have another model for that. It's called the valence shell electron pair repulsion, or VESPER model. And it's based on the number of regions of high electron density. So when we're talking about polarity, those lone pairs affect the shape of the molecule. And it can also be used to predict structures of molecules or ions that contain multiple bonds or unpaired electrons. So here are the shapes that y'all have to know. These are linear. They're in a straight line. This molecule is bent. It's a shape. And it's not indicated here, but usually bent has 2 lone pairs. Sometimes it can have 1, usually 2. This is trigonal planar. This is trigonal pyramidal. Sometimes they just call it pyramidal. And it's kind of bent down. It's not flat like trigonal planar, because usually there's a lone pair up top, like that ammonia molecule you saw back. This is tetrahedral. And this one is trigonal bipyramidal. Now, this middle is the center atom, and usually the whites are atoms, but with trigonal bipyramidal, this could also be a lone pair, and this could also be a lone pair. It just depends on what it's bonded to. Now here at the bottom, there's this website. There's some really cool animations, and you can see it in 3D. It rotates. So you could go there, but just remember, he's got a lot more on there. Just remember, these are the only 6 that y'all need to know. Okay, so let's draw some of these Lewis structures. So we've got PO43. So this is phosphate. So I need to add up all my valence electrons first. So I have 1 phosphate, and I have 4 oxygens. So phosphate has 5 valence electrons. Each oxygen has 6 valence electrons. So that's 31 valence electrons. I hope my math is right. It's early. Okay, but this is an ion, right? It has a 3- charge. So I need to add those electrons to my total. So I need 34 valence electrons around here. 24 and 5 is 29. Wow. Okay. How about we need 32 valence electrons around phosphate. So I'm going to put the least electronegative atom in the middle, which is phosphorus. And then I'm going to bond all my oxygens around it. Now in doing that, each bond is worth 2, right? There's 2 electrons here. So 2, 4, 6, 8. I've used up 8. I've got 24 to go. I can only use these 32. I can't just add in, and I can't just subtract from it. I've got to use all 32 in this drawing. So I've used up 8. I got 24 to go. So I'm going to start putting them around the oxygens so that everybody's got 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, and since this is an ion, I'm going to put it in brackets and indicate that it has a charge. And then I'm going to calculate my formal charges and make sure they're low and that I have any positive charges on a very electronegative atom. So we said phosphorus had 5 valence electrons, and now it's got 1, 2, 3, 4 bonding pairs on it. No lone pairs, so the formal charge of phosphorus is 1. Which is okay because it's not a very electronegative atom. Okay. Oxygen has 6 valence electrons. It has 1 bonding electron, so -1, and 1, 2, 3, 4, 5, 6 pairs, so -6. So it's a -1. And that's okay for oxygen to be negative because it's a very electronegative atom. Now if we had calculated this and oxygen had a +1 charge around it, then we knew that tells us we've drawn our structure wrong and we need to maybe create a double bond or do something else. Let's try this oxygen. 1 bonding electron, 6 valence electrons, and 1, 2, 3, 4, 5, 6 lone electrons, so -1 charge, and both of these oxygens are the same. Okay. So we'll just write those right by them. Okay, NH3. So first we need to figure out how many valence electrons we have, how many we need in our structure. Nitrogen has 5 valence electrons. Hydrogen has 1 valence electron. So we need 8. Now there's no charges, so we don't need to add or subtract anything. So I've got to use 8. So the least electronegative goes in the middle, which you think would be hydrogen, but hydrogen never ever ever goes in the middle because it only has 1 valence electron. It can only create 1 bond. So it never ever goes in the middle. So nitrogen goes in the middle, and then we're just going to bond all our hydrogen around it. Okay, and we used up 2, 4, 6 electrons so far. We got 2 more to go. So can I put 2 electrons on these hydrogens? No, because they are full up. But nitrogen has got 2, 4, 6 around it. And remember the octet rule, everybody wants 8 except for hydrogen because it just can't hold 8. So nitrogen needs 2. So now it's got 2, 4, 6, 7, 8. So we've got 8 around our center atom. And our hydrogens are full up. They each have 2, so then we're done. So now we just got to calculate our formal charges. Nitrogen has 5 valence electrons, minus 1, 2, 3 bonds, minus 1, 2 lone pairs, which gives it a formal charge of 0. Hydrogen has 1 valence electron and 1 bond, 0 for each. Now they won't always all be the same. So these are all 0. So that means it's a pretty good structure. Everything's pretty low. Alright, carbonate. Again, we need to calculate our valence electrons. So we've got a carbon, 3 oxygens. Carbon has 4 valence electrons. Each oxygen has 6 valence electrons. Let's see if I can add this one up right. 18 and 4 is 22. So I have 22 valence electrons to work with, but this is an ion, so I need to add these 2 to it. So really, I've got 24 electrons to work with. So my least electronegative atom is going in the middle, and then I'm going to bond my oxygens around it. Okay, so I've got 1, 2, 4, 6 left. So I got 18 to go. Not 8. Yeah, I got 18 to go. Lord. Okay, so first I need to satisfy my center atom. No, that's not right. Do your center atom last. Sorry. I'm going to satisfy the octet of all the oxygens first. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so I'm out of electrons. I can't use any more up. Now my oxygens all have 8, 2, 4, 6, 8 around them, but my carbon doesn't. It just has 6. So one of these oxygens has to share because everybody wants 8 electrons around them except for hydrogen. Hydrogen only needs 2. So what I'm going to have to do is form a double bond where oxygen is we're going to take these electrons and we're going to share it and create a double bond. So I'm going to put these electrons here. Now everybody is happy. Oxygen has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and carbon has 2, 4, 6, 8. Okay, but now I've got this double bond here, and I can write resonance structures because the double bond doesn't necessarily have to be between that carbon and that oxygen. It could be between this carbon and oxygen, or it could be between this oxygen. Alright, so let's calculate resonance, or we already drew resonance. Let's calculate formal charges, and we have to do it for each atom on each resonance structure. Okay, so carbon, we'll do this one first. On carbon, we've got 4 valence electrons and 1, 2, 3, 4 bonding electrons, no lone pairs. So the formal charge on carbon is 0. On this oxygen atom, we've got 6 valence electrons, 1 bonding electron, and 1, 2, 3, 4, 5, 6 lone pairs, which gives this oxygen a -1 for a formal charge. This oxygen down here is going to be the same. This oxygen over here is 6 valence electrons, 2 bonding pairs, 1, 2, 3, 4 lone pairs, and this gives us a formal charge of 0, which is okay for an oxygen to have 0. Now if it was +1, then we need to find a different structure and see if we can maybe draw a different structure, because oxygen should never have a +1 formal charge. So down here carbon will be 0, this will be -1, -1, 0, this one will have 0, 0, -1, -1. Okay, intermolecular forces. There are 3 types of intermolecular forces, or IMF. The first 2 are called van der Waals forces, and sometimes they're just categorized together. They're basically dispersion forces. So London dispersion force is between nonpolar covalent molecules. So this would be something like a diatomic molecule like N2. Now electrons kind of move around, and so if we've got 2 molecules, because we're talking about intermolecular forces, so attractive forces between these 2 molecules, these electrons move around. So sometimes these electrons could be over here, which leaves this open to be like a positive, kind of give a positive charge. Whereas these electrons could be right here, and you get a negative charge, and you get this attraction. These only last for a second. This is an extremely weak force, very weak. Then you have dipole interactions between polar covalent molecules. So that would be like our ammonia molecule. That's the lone pair. I wish I had chose hydrogen. So like this is this dipole moment is kind of positive on this end. This is negative down here, right here, the negative, and so they're attracted to each other. This is a little stronger than the London dispersion force, but not much. Now hydrogen bonding between covalent molecules that have hydrogen attached, which I kind of did here, but like I can't draw. Like water. Water has hydrogen bonds. Oxygen is extremely electronegative, so you get a super strong dipole moment. And so like this hydrogen would be attracted to this oxygen. And if I had this water molecule, this oxygen is attracted to that hydrogen. And this hydrogen would be attracted to this one. And so you get these super strong dipole moments. So this is the strongest intermolecular force. And DNA is held together by hydrogen bonding. So it's a very strong intermolecular force. Okay, so if you're confused, watch the tutorial again. Make sure you write down questions that you have for me in your C notes. That's why you take C notes. Write questions you have for me on the left-hand side.